Hello, everyone. Today, our team, one Astrid, consisting of me, Yitong, Shuzhen, Xingyu, and Jing, is going to show you how to design the most cost-efficient beverage can possible. Now, you might be wondering, why are we doing this? Why does a tiny change in a beverage can matter? To understand our motivation, let's look at the massive economic problem that beverage companies face today. Global giants produce hundreds and billions of cans each year. To make these cans, they rely heavily on aluminium. Now, aluminium is a fantastic material. It's lightweight, durable, and infinitely recyclable. But it has one major downside. It is incredibly expensive to source and process. When you are manufacturing on a global scale, even a fraction of cent saved per can adds up to millions of dollars. Conversely, any waste materials cause production costs to skyrocket, eating directly into company profit. And that is exactly the problem we are here to solve. We are proposing a design methodology to help these companies produce the exact same massive volume of high quality cans, but still using significantly less material, which is aluminium. The secret isn't changing the recipe of the drink or making the can weaker, okay? The trick is pure mathematical optimization, shaping the can so that it can hold the exact same amount of liquid, but requires the absolute minimum amount of metal to casing it. So how are we gonna do this? Well, our objective today is to calculate the precise dimension of a cylinder to minimize its total surface area while keeping the internal volume fixed. To make this work, we're using four key assumptions, which is that the can is a perfect cylinder. The aluminum thickness is perfectly uniform, and the manufacturing defects are ignored, while also the internal volume is strictly constant. And by reducing the surface area, we slash the amount of expensive aluminium needed. Okay, now I will now pass it over to my team to show you how we make this happen.
Hi everyone, my name is Lim Sin Yu and my student ID is TSC2509074. Before solving this optimization problem, we first identify the relevant calculus 2 concepts and understand how they are applied to develop the mathematical model. In this project, we mainly applied three concepts: function of two variables, partial derivative, and optimization with constraints. I will explain each concept and demonstrate how it is applied to develop the mathematical model of the beverage can. The first concept is function of two variables. A function of two variables is a function that depends on two independent variables rather than just one. Its general form is fxy. In this project, we will apply this concept to model the surface area of the beverage can. To apply this concept, we first make two assumptions. First, the beverage can is modeled as a closed cylinder. Second, the thickness of the can material is assumed to be negligible. Next, we define the radius as r, the height as h, and the surface area as s. Based on this assumption, the total surface area of the can be expressed as 2 pi r squared plus 2 pi r h. Since the surface area depends on both r and h, it is considered a function of two variables. The second concept is partial derivative. Since the surface area function contains two variables, we use partial derivative to analyze how each variable individually affects the surface area. The partial derivative with respect to r measures how the surface area changes when only the radius changes, while the height remains constant. Similarly, the partial derivative with respect to h measures the effects of changing only the height. This idea provides the foundation for the optimization process in the next section. The final concept is optimization with constraints. Optimization is the process of finding the best possible solution under a given condition. In this project, our objective is to minimize the surface area because the amount of aluminium used is proportional to the surface area. Using less material helps reduce the manufacturing costs. However, we cannot simply make the can as small as possible because it must still hold fixed volume of beverage. Therefore, the volume of the can becomes our constraint. The volume of a cylinder is given by V equals pi r square h. To simplify the optimization problem, we use the constraint equation to express the height in terms of the radius. H equals V over pi r squared. Next, we substitute this expression into the previously defined surface area formula. After simplifying, we obtain S of R equal 2 pi r squared plus 2V over R. As a result, the surface area is expressed as a function of a single variable, which prepares the model for optimization. At this point, we have successfully identified the relevant calculus 2 concepts and developed the mathematical model. Next, my teammate will apply partial derivative together with the volume constraint to determine the optimal dimensions of the beverage can.
In the previous section, the surface area of the closed cylindrical can is given by 2 pi r squared plus 2 pi r h, where r is the radius of the can and h is the height. We first find the partial derivative. Taking the partial derivative with respect to the radius, while assuming the height as a constant, we get 4 pi r plus 2 pi h. Next, taking the partial derivative with respect to the height, while assuming the radius as a constant is 2 pi r. As discussed by Xingyu, the volume constraint can be rearranged to express the height in terms of the radius. Substituting this constraint into the surface area equation reduces the problem from a two-variable function to a single variable function. Now, we can perform the optimization calculation. First, we differentiate the surface area function with respect to r. 4 pi r minus 2v over r squared. To find the critical point, we set the first derivative equal to 0. Rearranging the equation, we get 4 pi r equals to 2v over r squared. Then the optimal radius is v over 2 pi power of 1 over 3. Next, we find the optimal height by substituting the radius into the volume constraint. After simplifying, we obtain h equals to 2r. This means that the optimal height of the beverage can is equal to its diameter. To confirm that this critical point gives the minimum surface area, we use the second derivative test. The second derivative is 4 pi plus 4v over r cubed. Since the second derivative is always greater than 0, the critical point represents a minimum surface area. Now, let's look at a work example. Assume the beverage can has a fixed volume of V equals to 330 cm cubed. Using the optimal radius formula, we obtain R equals to 3.74 cm. Since H equals to 2R, the optimal height is 7.48 cm. Therefore, for a 330 cm cube beverage can, the most cost-efficient dimensions are approximately radius equals to 3.74 cm, height equals to 7.48 cm. This example demonstrates how calculus optimization can determine the dimension that minimize material usage while maintaining the required volume. Now I will pass it to my team member to continue the next part.
Hi everyone, now let's interpret the result. So first, from the partial derivative, we observe that the surface area is more sensitive to change in the radius than the height. So this means that changing the radius has a greater effect on the total surface area because it influences both the top and the bottom surface as well as the curved surface. So after applying the volume constraint, we obtain the optimal ratio, which is h equal to 2r, means that the height is equal to the diameter. So at this ratio, the radius and height are balanced and giving the minimum surface area while maintaining the required volume. So as a result, using the less material and can leading to the lower manufacturing cost and improve the material efficiency. So this optimization also can be applied in several real-world situations. And the first one, in the beverage manufacturing, a company can optimize the dimensions while maintaining the same beverage volume. So this can help us to reduce material usage and manufacturing costs. And the second, in the packaging industry, optimization improves the packaging design and production efficiency by using material more effectively. And last one, they are important for the environmental benefit, and using the less aluminium reduce the resource consumptions and carbon emissions and can support our more sustainable manufacturing. So although our model provides the effective solutions, but it's still based on the several simplifying assumptions. So first, our model shows that our can is the perfect cylinders, whereas the real reality, our beverage cans have the curved top and the bottoms. So the second, we also assume that our materials have the uniform thickness, and actually, our cans usually have the thicker tops and the bottom for the strength. And also, we also ignore the manufacturing constraints, such as the machines and mold limitations, as well as transportation and storage considerations. And to improve this model, our model can include our curve can be shapes and different material thickness, additional cost factors, and more advanced optimization technique. And to conclude it, our study demonstrates and that our calculus concept how to can apply to solve the real engineering problem. So from the partial derivative, we found that the radius have a greater influence on the surface area than the height. So after applying the optimizations with a fixed volume constraints, we determined that the optimal ratio, which is h equal to 2r, can minimize the surface areas. So this shows that the more efficient material usage and lower manufacturing costs. So besides the beverage cans, this optimizations approach can also support the better engineered product design, reduce the material consumptions, and contribute to more sustainable manufacturing. So that is our group presentations. Thank you.